All right, now that we've reviewed some redox topics, we're going to go deeper into electrochemistry. So redox creates energy and heat can be produced, and electricity can be produced if you separate the reactants from the products like we did in this diagram down here. And this is just kind of explaining it. So we talked about the salt bridge that allows the ions to flow, and the electrons are going to travel through the wire in order to create that electrical conductivity. There's a few vocab words here too that I want to highlight. There's a galvanic cell and electrolytic cell. And these are basically just backwards of each other. So a galvanic cell is one where you use chemical energy. So it's a chemical reaction that changes into electrical energy. So that's what we did in that diagram where oxidation happens at the anode, reduction happens at the cathode, and you get that flow of electrons. An electrolytic cell is the opposite, where you use electricity to force a chemical reaction to occur that is not spontaneous. So for a galvanic cell, you're starting with the chemical reaction and getting electrical energy from it. Electrolytic cell, it's hard to say, is using electricity to force a non-spontaneous reaction to occur. So just keep those in mind. I've seen questions about those on the AP exam before. And we're going to learn about that EMF, the E cell. We're going to learn how to calculate that in just a few minutes. There are a whole bunch of pictures and diagrams in your textbook, so if you're curious about how all this works or you want to see more pictures and diagrams, all of these have been taken from your textbook, and you can easily see how all of this is going to work. This is just another one. It's very similar to the one that I drew over on the side that's showing you how the electrons are flowing, how the electrodes are changing, the spectator ions, all that kind of stuff. All right, let's get to how to calculate the electrode potential. So you're going to have a list of potentials that's actually on page 845. This has the reduction potentials. And what I mean by that is you're going to have a full list of reactions like this. So copper 2 plus going to copper solid, cobalt 3 plus going to cobalt 2 plus. So all of them are reducing, not necessarily down to their neutral solid, but they're going from a higher charge to a lower charge. And it gives you the volt for each volt amount for each one. So notice that copper is 0.34 and cobalt is 1.82. And so what you're going to use for this, so you first have to find the reduction potentials, and it might be that you have an oxidation reaction, and so you're like, well, it's not on there. You just have to keep in mind that every reaction on there is a reduction half reaction, that they're not, there aren't any oxidations on there, so you just flip it and you can change the sign of the volt. And the rule is that you need to have a positive voltage once you add them together. So you're going to have to, so here's what I'm trying to say. If you're, these two black reactions that I have over on the side, if they were going to happen and you were trying to get electrical energy from them, one of them has to be flipped because you can't have two reductions. You have to have one reduction and one oxidation. So the way that you decide which one to flip is the one that will make it so that when you add them together, you still get a positive voltage. And remember, when you flip the reaction, you're going to change the sign just like for Hess's law. So if I flipped the second reaction and had a negative 1.82 and add that to positive 0.34, I would get a negative number, and that means I wouldn't get any electrical energy from that. So that's not what I'm going to do. So what I'm going to do here instead is to flip this one so that this becomes my oxidation. And now this becomes a negative 0.34, and then we can add those together. And so the E cell is going to be 1.48 volts. So the math is not bad, you just add them together. The main thing is you just have to be able to figure out which one you're flipping. And again, you want to flip the one so that when you add them together, you still get a positive value. Now you still do need to balance the electrons and balance the reactions. So notice that cobalt is gaining 1 electron to go from 3 to 2, and copper is donating 2. And so we are going to have to multiply this reaction by 2. So we're going to have a 2 here and a 2 here so that the electrons will cancel out. However, here's the catch. Pay attention. Do not multiply 1.82 by 2. So this is not like Hess's law. The only thing that's similar about this to Hess's law is that when you flip a reaction, you change the sign. But the coefficients do not affect the voltage. So our final reaction here would be 2CO3 plus copper solid yields 2CO2 plus copper 2 plus. And again, the E cell for this reaction would be right here. All right, let's go back over here, and you need to know how to do the line notation, which is a way of showing what's going on in these electric cells. So first of all, you're always going to put the anode on the left and the cathode on the right. Just think of it as if you're putting them in alphabetical order, so A comes before C. The line is going to represent the separation between the two things that are changing. So in this case, magnesium 2+, and then you also have aluminum 3+ and aluminum. You're going to have a double line in the middle that represents the salt bridge or the porous disk in the middle. And notice that you include the states of matter, you include the concentration if it's aqueous, and it doesn't say this, but you put sorry, can't use my words and write at the same time. You put the electrodes, the solid electrodes, on either side of the line notation, so they'll always be on the outside. And there's a few more rules down here that you want to make sure you read through these carefully, and definitely look at this example on page 849. But these are the rules for a galvanic cell. The cell potential, and what I mean by that is this E cell over here that we calculated, has to be positive. The direction of the electron flow is going to be shown on your picture, so you want to make sure you can show the arrows to show which way the electrons are going. Make sure you can write the anode and the cathode. So anode is going to be on the oxidation side, cathode will be on the reduction side. You also need to make sure you label the electrodes, and sometimes you won't have an electrode because over here we're going from a cobalt ion to another cobalt ion, and both of those are in the solution because they're both ions, so there's no solid cobalt electrode that's going to be in there. And so instead you're going to use platinum. So anytime you have two ions that you don't have a solid for, make sure you use PT as the electrode. And that's what it says right here. And if you end up with H+ in the final reaction, then you should put H2SO4 in your line notation. All right, let's do some of these calculations down here. So we're going to include a new constant called Faraday's constant. And this is on your reference packet. It's a big number, 96,485 is the number of coulombs per mole of electrons that happens. So this is going to talk about the amount of electrical energy that we're doing. And we're going to use this in an equation in just a few minutes. But before we get to that equation, I want to highlight this right here. This will help you out a lot in this chapter. If you can remember that a volt is the same thing as a joule per coulomb. A volt is the same thing as a joule per coulomb. We're going to use that in just a few minutes. There's a few things that I jotted down over here on your list. The more positive the E cell or the voltage, the more likely it is to be reduced, and the more negative ones are more likely to be oxidized. And this is just explaining what I did up there. This right here is explaining what I did up there, that you are going to add the cathode and anode together, but don't forget that you have to flip one of them, which means you're changing the sign of one of them. And this is the next equation that we're going to talk about here. So the rest of those equations are just kind of showing how they derived that. So you've got your maximum work is related to delta G, and then they kind of included all these reactions or all these equations to get to that final one. But this is the one that we're going to focus on. Delta G naught equals the negative N, which is the moles of electrons transferred, times Faraday's constant times the E cell. So let's go over here and we're going to do that for this equation. So if they wanted you to calculate the Gibbs free energy for this, the moles of electrons here is going to be 2. So that is the number of electrons transferred. So notice that cobalt only lost 1 electron, but then we had to multiply it by 2. So it's actually 2 electrons. And then copper went from 0 to +2. So copper is losing the 2 electrons. Cobalt is gaining 2. And so down here, this number is going to be 2. Oops, got a negative. There we go. And then you're going to plug in Faraday's constant, which is given to you in the reference packet. Times the E cell, which we calculated in the black box up there, so 1.48 volts. And you just multiply them all together, and that will give you your delta G. And notice that if we're checking our units, so this was moles of electrons, instead of volts, I'm going to use joule per coulomb. Remember that's over here in that green box over there. So notice that moles of electrons will cancel, coulombs will cancel, and we'll be left with joules. So the unit for your final delta G is going to be in joules. Also, notice that if you plug in a positive E cell, which you have to get a positive E cell if you're getting electricity, then because of that negative sign in the equation, you're always going to get a negative delta G, but that's exactly what you want, because remember, when delta G is negative, that means it's a spontaneous reaction. So E cell is positive, delta G is negative. And that is it for today. We already did these yellow sticky notes. In case you're wondering, I did that up at the top. So try that progress check, and we will go over any of this in class if you have questions.